Use the normal approximation to calculate the probability that x is greater than or equal to 17 for n equals 30 and p equals 0.5. So I underline normal approximation because that's a very important phrase. It means we're going to use the bell curve to approximate this binomial probability. This is a very useful technique because when you look at sample sizes like this of 30, we notice that our tables don't typically go up that high. Most binomial tables will go to 20 and then they'll skip a bunch of values and just give you n equals 25, but they don't have anything between 20 and 25 typically, and they don't have anything after 25. So when you have n is 30, you're kind of stuck because at that point, you don't know where to get the probabilities from. Of course, you can use software. Software is a preferred choice these days. It's so readily available, but if you don't have software, you can use this normal approximation technique to be able to solve the problem. And even in the case of software, sometimes the software will have a faster time doing the answer if it can use the normal approximation technique instead of using the true binomial probability to do the answer. Okay, so let's look at how this is done. We're going to draw a bell curve, of course, because we're using the normal approximation implies we're using a bell curve to answer the question. So we'll definitely have a bell curve. For all bell curves, we're going to need to have a mean and a standard deviation, right? Well, the mean here should be the mean for the binomial random variable, which is defined as n times p. So in our case, n is given to us as 30, so we're going to say that's 30 times 0.5. 0.5 is just 0.5 as a decimal, or 1/2, so of course the answer here turns out to be 15, half of 30, right? So we know the mean is 15. So I'm going to put a z-axis down here and an x-axis. Remember, x represents the number of successes. We're saying the average number of successes here should be 15 when n is 30, if the probability of a success is 50%. Okay, now the standard deviation for the problem is going to be the square root of n times p times q. These are formulas from back in Stats 1 where you learned the binomial probability formula. So n times p times q gives us the answer. All right, now, n is going to be 30, right? P we just said was 0.5. Q has to add to P to give you 100%. So if you have 50% for P, you must have 50% also for Q. So the two of them add up to 100%. So we're basically going to get the square root of, this is 15, then half of 15 is 7.5. We'll have the square root of 7.5 to work out. Let's do that now and see what that is. So the square root of 7.5. When you do that, you get the answer 2.73, let's say 9, just to get it out to 3 decimal places. 2.739. So 2.739 becomes our standard deviation. Now let's think about what we're asked to do. We wanted to find the probability that x is greater than or equal to 17. So if I put 17 on this side of the curve here, right, I'd be looking for the probability that x is from that number or above, right? So greater than or equal to, greater than would be this tail. At this point, it would look just like a normal bell curve problem, and we would run off to our formula for the z-score, convert 17 into a z-score, and then we would, once we're done with that, we would go look that up on our z-chart and we'd get our area, and a piece of cake, right? No problem at all. Except for, there's one little trick to this procedure which you have to remember to do. The trick is that you have to do something called continuity correction. Continuity correction. In order to do that, what you basically are going to do is you're going to think, well, if I want to accumulate area from here over to the right, I have to be very careful that I don't, start in the middle of a rectangle, because we have to remember that if this was the binomial distribution, the actual drawing for that would look like this, right? Let's say there was a 15 here, there'd be a tall rectangle, let's say, right? And then there'd be, say, 16 right here, and then about here there might be the rectangle for 17, so on and so forth. And let's just say, for argument's sake, that this kind of looks like this when you do the drawing, right? Let's just say that it kind of looks like this. All right, well, if we were to start to go, like, say we're going to get, all the area from 17 and above, if we start right at 17 and go up, right, to find all this area, we're actually chopping half of the rectangle for 17 off, because we know this actually goes down to 16.5, right? The number smack in the middle between 16 and 17. That's how the rectangles are when you're dealing with a discrete random variable. So basically what we have to do is not start right at 17. We actually have to start a little before it. The way I always thought of it was like if I was trying to sweep up a pile of dirt to the right, I wouldn't stick my broom right on the pile. I would stick it a little before the pile on the floor and sweep to the right, right? I would not stick my broom right on the pile and knock the dust around. So I'd have to start just a little before to make sure I got all of the material. So that's what we have to remember, is that we're actually not going to look up 17. We're going to look up something right before 17, and that number that we're going to look up instead will be 16.5. So you have to take a 0.5 away from the number you're looking up. Why the 0.5? Because remember, that's where this rectangle for 17 actually begins, right? Then if we sweep over to the right, we'll get all of the rectangle for 17 and all the rectangles after it. So it's going to be this number that we convert to a z-score. All right, so the z-score formula, remember, is x minus the mean over sigma. So for us, the x here is 16.5 minus the mean, which is 15, over sigma, which is 2.739. All right, once you do that, you'll have your answer for the z-score, and the rest is just looking it up on the table. So we'll have 16.5 minus 15. Of course, that's going to give you 1.5. And we'll divide that by 2.739. And we get the answer 0.55 if we round to 2 decimal places, which is going to be necessary for our z-table, right? Our z-table doesn't have more than 2 decimal plations. When we look that number up, remember, we're going to get from here to here. That's not the number we want, so we'll have to do 1 minus, right? We'll do 1 minus, we'll do 0.5 minus that answer to get our final solution. All right, let's first go to the z-table though and look up 0.55 to get the area from here to here. Okay, so we're looking up 0.55 on the z-table. There's 0.5, and over to where it says 5 here is 0.2088. 0.2088. Okay, so the answer was 0.2088 from our table, and we're going to take that value and subtract it from 0.5 to get the area in the tail. So we do 0.5000 minus 0.2088. And when you do your subtraction, of course, you'll do some borrowing here. You get 10 minus 8 is 2, 9 minus 8 is 1, 9 minus 0 is 9, and 4 take away 2 is 2. So the answer is 29.12%. So the probability then, for our question, the probability that x is greater than or equal to 17 is approximately equal to 29.12%. And that's the answer you get using normal approximation.